Welcome to Lesson 2 on configuring the ScreenOS firewalls. In this lesson, we're going to go over the ScreenOS concepts, terminology, and the platform. We're going to relate the architecture and the setup in ScreenOS to those you may be familiar with that are used in a standard firewall configuration. So the concepts, objectives for this lesson are to be able to describe the requirements that a firewall has to implement. And these, of course, will be fulfilled by the ScreenOS architecture. We will then take a look at how ScreenOS is set up and how it maps its architecture to deliver the requirements of the generic firewall. And then we will take a look at specifically how the packet flow works in a ScreenOS architecture. This will be fundamental to all of the further configuration and setups that we'll be doing throughout the rest of the course. So the packet flow is probably the most important thing to really get down and understand out of this lesson. Then finally, we'll take a look at the variety of the ScreenOS devices in the portfolio and explain how they map to the requirements you might have in designing networks that would require firewall protection, which devices are used for which services and for what reason. So these are the major concepts and objectives that we have in this particular lesson. The first part of that then is to take a look at what is a firewall. Not specifically ScreenOS, but this is all simply the requirements that any firewall would have to have in a professional environment. So the requirements for a firewall are: you have to be able to do frame packet forwarding, bridging and routing. So underneath everything that a firewall does and that makes a firewall, it's still a router. So, and a switch. So they're operating both at layer 2 and layer 3 to provide switching and routing on the network. The second area that is a requirement to be a firewall is to have stateful inspection. This is where we take a step above being just a simple router. We are able to maintain a session table so that we know what connections are actually coming through. In a router, we're simply looking at each packet as it arrives, making a routing decision and forwarding it. Well, in a firewall, we're comparing the packets that come in to those that have come before, and we're understanding the actual data flow that's happening in the network. And then after maintaining the sessions, we can inspect them. And then we can do filtering and apply rules to those connections. Allow some, deny others, or only provisionally allow, depending on a wide variety of items, port, IP address, or other things of that nature. So this stateful inspection is what makes a firewall and not simply a router. The next major feature that firewalls have to provide is address and port translation. Network address translation is a big part of how firewalls manage to allow access to the general internet for devices that are on a private network. There are only certain addresses, of course, as you know from your IP, that are routable on the internet. The private addresses have to be converted to public addresses via address translation before going out. That's the job of the firewall. The second part of the firewall is to do port forwarding. And in this case, the address translation is usually coming in the other direction then. We have private resources on our private network that we want to make available to those on the internet. So we have to bring in the traffic that hits the firewall and forward the specific ports for whatever that application is to the correct device. So this address translation, port translation are important functions for an operating firewall. Then the fourth major category that firewalls have to provide in general are VPN. standardized under the IPsec rules. These allow point-to-point tunnel connections to be created between two devices that are a private connection but are transferred over the public internet network. So these are the four major conceptual areas that a firewall has to provide in order to be a firewall. Now we're going to take a look at each one of those four in turn in slightly more detail. So with layer 2 frame forwarding, we're basically talking about switching here. So in order to be a switch, your firewall has to be able to learn MAC addresses. And in learning those MAC addresses, it will associate MAC addresses with particular ports on the firewall and build a table of those addresses. Based on this address learning, then, the firewall will forward ARP MAC requests to the correct port. And if it doesn't know the destination of a layer 2 request, it will flood it out all of the ports. Basic Ethernet layer 2 that you are all familiar with. So these all have to be implemented in the firewall. Then the last thing on layer 2 that needs to be implemented in the firewall is a method of loop prevention, as we all have no doubt experienced when someone takes one of those wonderful unmanaged switches and connects a layer 2 loop together on our network. If you don't have loop prevention protocols in place, things can get out of hand pretty quickly in a broadcast storm. So spanning tree and loop prevention are an important feature that have to be present on the firewall. So this is our basic diagram of our layer 2 network. We have 2 ports, Ethernet 00 and Ethernet 08. We have 2 computers attached to those ports with MAC addresses ending in 5120 and CD10. And because of the various traffic that's occurring on our network, our firewall has built an address table knowing that those MAC addresses are attached to those ports. So in the event that the computer at 5120 wants to communicate with the computer at CD10, the firewall is able to directly forward and establish the switching between those 2 ports. So layer 3 then is our IP packet forwarding. These are also a requirement for being able to run a firewall, our router underneath. So we have to have our routing options available to us. The most basic routing option is, of course, being able to create static routes. Virtually all firewalls will allow this method to occur. So you can create a route, a statically addressed route, say this is the next hop, this is the network that gets there, and that's the interface to go out to get there. Many firewalls also support dynamic routing protocols, RIP, OSPF, or BGP. This is to a varying degree a difference among firewall vendors. You will find some more support and some with less support, but generally some kind of dynamic routing protocol could be supported on the firewall. These allow you, of course, to establish neighbor relationships and learn routes instead of having to manually program every single route on your network. And of course, your firewall also has to be able to accept a default route, so that if you don't know the network that the IP address is on, there's a default location for which the firewall will forward all traffic that it doesn't have a specific route for. So this is what our basic layer 3 might look like in a firewall implementation. Here we have 3 routers, X, Y, and Z, noted in the table here. And if host 1 on the left-hand side is going to send a communication to try to get to host 2 as a destination address, the router at X, which could be our firewall, knows that there is a connected network A and B, and it knows the C network by a static route and a forward. So when it sees that, it's going to forward the traffic to router Y to get to network C, because that's what it says is gateway is here. So network C is being forwarded to router Y. And then when it gets to router Y, we know network C, as we can see for router Y, is a connected network, so it will be able to deliver the packet. So layer 3, basic straightforward IP forwarding. This is a function that your firewalls will need to be able to support. The next major area that we want to support in our any firewall is stateful inspection of the traffic. So this means we're going to maintain a session table. We're not just going to simply review the IP packet and forward it, as we do with a router, but we're going to establish a session between two endpoints, and we're going to maintain basic information about that session. That information will include the IP address, the source and destination IP address, and what IP protocol is being used by that. That information will also include the type of traffic that is being forwarded, TCP, UDP, what port it is, and what port number is being used. So this all goes into then making up the session table. Based on the information that it gathers from this, it's going to implement the policies of the firewall. So the firewall will have rules written into it that will apply to the traffic. It will be either permitted or not permitted based on these rules. So this is what your general session table, a session table entry might look like. Where here we have a source IP address of 10.1.10.5. The destination IP address is the 117250, standard protocol 6, source port of 36,033, and a destination port of 80. And this is a type of HTTP request. So this then is established in the session. We know that this computer at 10.1.10.5 is making a web HTTP request to the server at 117250, and that is being logged and tracked in our session table so that we can inspect it and make sure that it is allowed by our policies before the traffic is forwarded through. Address translation and port translation, network address translation and port translation are our next feature for the firewalls. That previous traffic we saw was going from an internal address to an external address. Well, in order to do that, we sometimes have to convert address and port by configuration. So in this example here, we have a request coming from an internal source IP address, the 10.1.1.5, going to an external address, 2.2.2.2. Because that's going out onto the internet, it is necessary to translate the source IP address to a public IP address, in this case 1115. We see that on the first arrow there. So the network address is being translated. We also see in this case that the source port, the random port 44,235, is also being translated to port 30,777. The destination port is 53, a DNS request, and that of course has to remain the same for the request to go through correctly. So in this case, we're assigning a random port and an IP address to be able to have this routable on the internet. Frequently, this will of course be the interface port or IP address number on your firewall that translates to the IP of the interface and a random port in the high range. Standard network address and port translation for internet access. Your firewall will need to be able to do this, and of course the ScreenOS has a mechanism to do so. And our final feature that we're looking for in our generic firewall is virtual private networks. These create secure tunnels for information across the internet. They provide an encapsulation of the IP requests so that they don't have to be translated. The internal 10 addresses, or 192.168 addresses, or 172.16 addresses, can be encapsulated and sent across the tunnel. In addition, the payloads that are sent across the tunnel in a virtual private network are encrypted so that they can't be read while they're transiting the public network. And the VPN also then provides a method of authentication so that when VPN traffic arrives at our firewall, we have to be able to tell whether or not it's legitimate VPN traffic that we do want to receive, process, and forward on our network. So encapsulation, encryption, and authentication are all provided by the VPN services on your firewall. And this is an example of how that tunneling works. You have a gateway on each side of the VPN from one firewall to another. It establishes this VPN tunnel, then encapsulates and encrypts and passes this traffic across that connection to the other side. So there we have the VPN being established from gateway to gateway and the ability to pass traffic between two internal IP address networks, even across the public internet. So moving on now, here's our second section of this part of the program, is how are these features of a generic firewall implemented in the ScreenOS security architecture. So the ScreenOS architecture is made up of a number of components. It has a flexible and scalable architecture. On the low end of the scale, it's performing features in software, and as it moves up the line in the scales, it has hardware ASICs that a number of the features are implemented in order to perform line rate conversions of a number of features. So the components then of this architecture are interfaces, zones, virtual routers, policies, and virtual systems. These components interact with each other in a hierarchical method in order to provide a flexible feature set in the system. So what we're going to do is we're going to walk through the details of the relationships between these components over the next section of slides. All right, so looking at the specific architectural components in ScreenOS, we have these items here: interfaces, zones, policies, virtual routers, the forwarding table, a virtual system, a flow, and a session. So let's have a look at what that looks like. In the center of the image there is the rectangles that say root vsys, vsys1, vsys2, vsys3. All four of those virtual systems are in a single physical box. This is, in a sense, a virtualized network. An entire system is separate in its own operations. At the virtual system level, we can even have different administrative root logins so that they actually have control of everything within the virtual system itself. So in this scenario here, we have a number of bindings that are happening in each of the virtual systems. We show that there are some zones and some physical interfaces that belong to each of these different virtual systems. Virtual systems can have within them virtual routers. So one vsys can have multiple virtual routers. and then each of the zones gets assigned to a virtual router, and each of the interfaces get assigned to zones. Inside the system, then, we have collections of objects that are seen as being part of the same entity and collected together. So for instance, on the left-hand side here, we have our Untrust VR virtual router inside our root vSys. Inside of that virtual router, we have 3 zones: DMZ, Mail, and Untrust, and each of those castles represents an interface that is in that zone. So don't worry about the details of this now. This is a general layout that shows all of the features all at once, and now we're going to dive in at the lowest level and begin looking at how they relate together. Zone and interface assignments. So there is a strict hierarchical relationship between all of these objects within the ScreenOS architecture. At the top of the tree, we have the virtual system, as we just mentioned. The virtual system is the big piece, which can contain all of the other ones. Virtual systems are separate entities that can be managed and controlled administratively separately. Virtual systems can contain virtual routers. So your virtual router is a full firewall unto itself, but the root logon for the virtual system owns all of the virtual routers within it. So say in a typical ScreenOS SSG5 firewall where there is only one virtual system, you can have 3 virtual routers, all controlled by the same root login. Each router then owns the zone. The zone is owned by the router. The router is owned by the virtual system. Next down in the tree is the interface. So interfaces get assigned to zones, zones get assigned to routers, routers get assigned to systems. And finally, at the bottom here, we have the IP address. The IP address is assigned to the interface. So the interface must belong to a zone in order to get an IP address. If it's sitting off in null and hasn't been configured, then you won't be allowed to assign an IP address to it. Management services are enabled at the interface level. So if you want to be able to telnet SSH or use the HTTP or the SSL connections to the firewall, those are enabled at the interface level. So the interface can turn on the ability to use management protocols to the IP address on the interface, which is then part of the zone. Virtual systems. So at the top of this tree, we have the virtual systems. Each system can have multiple firewall devices emulated within it. So a single virtual system can have multiple virtual router firewalls. This is a way, virtual systems is a way for complete customer segmentation for a service provider. If you have multiple vSys available in your ScreenOS device, you can create a virtual system. You can hand over a root login to this virtual system to a customer, and you then don't have to make every single firewall change for them. So this is a hybridized way where they can make all the changes themselves but not actually own the firewall, and you can give them that login with full privileges on their system but no privileges on anybody else's system that's in your NetScreen device. Interface designations. On the different ScreenOS devices, there's a different interface naming convention set up for them. So on the ISG, the SSG, and the NS series of devices, they are generally labeled with the slash notation, the slot at the first number and the port on the second. So Ethernet 0/1 is the first slot, since of course, all good programmers start counting at 0. The first slot and the second Ethernet port on that slot. Ports, Ethernet ports and slots start counting at 0. So 00 would be the first one. Here we have another example of a serial port. If there's a serial port on the device, and say this would be serial 1/0, the second slot and the first serial device on that slot. So this is the common naming scheme for the ISG, the SSG, and the NS series. Now on the NS200, the NS50, the NS25, and the NS5GT, these are the older series of NetScreen firewalls. They will actually be labeled with the name Ethernet 1, Ethernet 2. They may also be labeled trust or untrust as the port name on the outside. But inside the interface they'll be spelled out, and there's no slot designation because there are no slots on this series of device. With the NS5GT, there is also the option to run what they call trust-untrust mode. So then the interfaces will be labeled trust and untrust. So these are the interface names that you will see in the configurations, and they will also be the names that you will have to use on the command line when you're configuring the device. Virtual interfaces. There are a number of interfaces that are not physical on the device, but are still interfaces that need to be configured and can be used for various purposes. So we have a VLAN interfaces. They are configured using the physical interface that you are going to have as the tagged VLAN port and a dotted notation. And then the tag that you want as the actual VLAN tag listed in the command. So Ethernet 0/1.1, Ethernet 0/1.2. Note specifically that the .1, .2, .3, those are not, repeat, not the VLAN tag. The VLAN tag is configured with the tag option. So it is not the tag, it is just a sub interface. The other virtual interface in the device is the loopback interface. These can be used to address the device without having the address assigned to a physical port. You can have multiple loopback addresses configured, so it's loopback.1, loopback.2, etc. Our next virtual interface is a tunnel interface. Tunnel interfaces we'll learn a lot more about during route-based VPNs. They could be bound to VPN tunnels and assist in allowing routing protocols to be sent across tunnels, and also have their own IP addresses and their own zone assignments independent of the egress gateway interface. So again, they're in dotted notation, the word tunnel.number, tunnel.1, tunnel.2, tunnel.3. And multi-link interfaces. ScreenOS supports multi-link for the serial interfaces that you can set up with frame relay or other serial protocols. And so those will be ml.number, ml.1, ml.2, ml.3. Interface configuration. Once we have interfaces designed, they have to be configured. So by default, all your Ethernet interfaces are going to have AutoSense, auto negotiation turned on, but that of course can be configured to be explicitly configured. There are serial interfaces available for T1, E1, and T3 that are usually plug-in modules then that would go into the slots in the supported devices. Wireless is available on a number of the models, so the antennas would be physically attached to the back of the device, and a virtual wireless interface can be configured and added to whatever zone and IP addresses are desired. And also there are ADSL interfaces available on the ScreenOS architecture. So those can be directly plugged in and connected to the ADSL networks. ISDN is supported as well, so an ISDN interface can be plugged into the slot and configured for the device. Stateful packet inspection. As all firewalls, ScreenOS is able to do the stateful packet inspection. It examines the content of the packet on the arrival to the ScreenOS device, and then it will look up the policies that are configured on the device and decide whether or not to allow or deny the packet based on the policy configuration rules that are available on the device. It will keep a session table of all those IP sessions that are currently not yet timed out, so that when further packets arrive for that session, they can be matched up to it. New packets are matched to the sessions, or a new session is created if there is no match. And if the session is permitted by policy, then the new sessions are created. This session ability of a firewall is, of course, at a much higher security level than straight packet filters. It's able to be aware of the communication that's occurring and can have more fine-tuned rules applied to that traffic. ScreenOS also supports a large number of application layer gateways. Application layer gateways make use of the session table information to provide special processing of the traffic as required. Application layer gateways are designed to be able to recognize protocol-specific behavior that occurs in traffic. An individual request and response command on a certain port or between certain addresses may require that dynamic ports be assigned to the session. So the application layer gateway is able to recognize that the dynamic ports being used are part of the session that should be permitted and not extraneous traffic that should be ignored or denied by policy. This allows the firewall to accommodate complex protocols automatically without having to write very, very difficult rules. It'll support opening multiple ports in both directions for a session, and it will also allow you to open and close what are known as pinholes per session. So if a session requires one of those random ports be open in order to be able to communicate, if you did not have the application layer gateway, you would have to leave all of those random ports open all of the time to allow that return connection. Instead, the application layer gateway opens the specific port being used by the specific session and then allows that traffic while the rest of the traffic is still blocked and the device protected. So the typical examples of what uses an application layer gateway would be file transfer protocol, H.323 or SIP. All of these protocols For instance, FTP will create its initial connection on a fixed port 21, but it immediately negotiates between the client and the server a random high port to do the actual communications and transfers on. By having the ability of the application layer gateway to recognize that an FTP session has been initiated, it will allow that higher port traffic to occur without having to have a broad rule that opens up the high traffic all of the time. So application layer gateways solve a fundamental problem of application communications being able to use random ports for specific sessions only. Attack prevention. Attack prevention is a screen function in ScreenOS. At the zone level, which are groups of the interfaces that are to be treated the same, there are profiles available that look for flood attacks, denial of service attacks, or other protocol anomalies and deny the traffic. There are a number of default screens available to protect the network from known types of attack, but they are configurable based on what you expect, the kind of traffic you expect to see in the zone that is in. So obviously more of these screens will be turned on an untrust type zone like the internet than on an internal network's trust zone. ScreenOS also provides a module for antivirus and anti-spam protection that can examine traffic and block based on signatures and the like. It also has a deep inspection ability where you can actually write signature profiles to identify traffic that you want to specifically block. So it allows to, and not just the port and protocol, but allows you to deep inspect the packet and block on very, very specific items. And finally, there's URL filtering available on ScreenOS through a number of methods. So you can do WebSense forwarding, you can use the web URL in a cloud type service, or you can configure whitelists and blacklists directly on the firewall. These services, the service-based ones, are also capable of recognizing known malicious URLs and blocking their entrance into the network. And the web filtering piece allows you to set up the local whitelists or blacklists, or use those cloud-based or WebSense external services for web filtering on the network. ScreenOS packet flow. This is the meat of how the process works in ScreenOS. So starting at the top left of the diagram, we have our inbound packet. The first thing that happens on arrival is ScreenOS will do a sanity check on the packet. This will verify that the packet is not malformed, that there's no problem with it that occurred in transition, and that it's a valid IP header and a valid packet that is able to be processed. Then the first part of the check will be whether or not the session for this packet already exists. It will take a look at the source and destination IP address, the ports in use, and it will decide if there is an existing session for it. We're going to say no on the first pass through here. So the first time a packet arrives, it needs to create a session. The process for doing that is to first look up the destination address. The destination address in the routing tables is going to tell you whether or not it is even reachable by this device. Now, because we have a default route, most things are going to be reachable by something, but if it does have some kind of black hole rule or some reason that there is no route to the address that is arriving, it will drop right at that point and reject the packet, and no session will be created. Once it's decided that the destination is readable, it looks where it's going to forward that packet. Because the destination is going to be forwarded somewhere, that interface is going to belong to a zone, and then that zone is going to trigger the policy lookup. So the source address and the source interface that received the packet will be the source zone, and the policy lookup will occur based on the destination address zone. So we have a from zone to zone, we look up the policy. If the policy does not exist, the default action is going to be not to allow it. So if it's if there is no policy, it will be dropped. If there is a policy for it, we are going to ask whether or not the policy permits that. It could be a permit policy or deny policy. If it's a deny policy, we drop the packet. If it's a permit policy, we'll go down to the forwarding operations. We might have to do an ARP query to see where to go. If it's a locally connected network, we might have to perform whatever action is required in the policy, and then we're going to add the session to the table so that it's available for the next lookup. So we've gone through this whole chart now, and we've added a session to the table. Now when the second packet arrives, it passes the sanity check, and there is an existing session, so it will simply forward and perform any actions that the policy is asking it to. The policy could be asking it to do some NAT operations. It could be asking to do any number of things. It could be associated with an application layer gateway. But whatever policy action is associated with that session will be immediately performed. As you can see then, the steps for the second and subsequent packets are much faster through the system. So this is our basic packet flow. We look up the zone where the packet arrived. We look up the zone where we are forwarding it based on its destination. We check it against the policy to see if it's permitted or denied, and then we create the session with all the actions necessary for that session. So let's take a look at a specific example of how the packet flow works in ScreenOS. Here we have a basic internal computer at 10.1.25 looking to go to a web server out on the internet. So the first question that's going to be asked when the packet arrives at the firewall there at 10.1.21 is, does the session exist? If the session doesn't exist, it's going to start doing its lookup. Is the destination reachable? Yes, it is. It's an internet website, so we have a default route for it to go to. Is it an interzone traffic between two zones? Yes, it is. It's going from a trust internal zone to an external zone. So we're going to look for a policy from trust to untrust to allow this traffic. So now we check that policy. That policy, there is an internet access policy. It is allowed by policy. So we're going to go ahead and process what happens on that policy. Are there any special actions? Well, yeah, we're going out on the internet. So we're going to NAT to the firewall interface 1180 and then take the private address off of there, the 10.1.25, and we have a NAT operation in this policy before it sends it off to the web server on the internet. So this brings us then to the completion of the packet flow example that we've performed all the way through all the actions necessary. So the next section on our agenda is to take a look at the specific ScreenOS platforms that are available to implement and what situations the different platforms would be used for. The ScreenOS platforms break down to a number of levels. We have the SSG series. This is Secure Services Gateway. These are for small office or the enterprise use. There are a number of devices in this series. They have one virtual system in them, and usually three virtual routers, but there are models, larger models, that have more. So at the smallest end, we have one virtual system and three virtual routers. These are typically deployed in enterprise network situations or small office, home office. The NS series is capable of larger scale traffic and can have multiple virtual systems. So for a large enterprise with a data center or a large home office that might want to have multiple virtual systems segmented off to multiple administrative departments, or a small service provider building a cloud type architecture in a data center that wants to be able to segment off by client. And then there's the ISG series, the Integrated Security Gateway. These are service provider class devices, much higher traffic levels, much higher numbers of virtual systems available, lots of card slots available for expansion to have many interfaces in them. So these are the progression up the chain of the gateway. The SSG series for the medium, small enterprise and home office, small office. The NS series for the small service provider, large enterprise, and the ISG series aimed at the service provider market. These are the SSG line in particular. They range from the SSG 5 up to the 550M. And what's listed on the slide here are the number of interfaces and their type that are built in to the device and the amount of traffic that the device is capable of handling in total and the amount of VPN traffic that it's capable of handling. So for example, the SSG 5 has 7 fast Ethernet, that's 100 megabit interfaces, and it can handle 160 megabit per second of traffic and 40 megabit per second of IPsec VPN traffic, with the overhead of encrypting and decrypting and all that goes with it. So as you can see, as things move up the line, the capabilities in the number of interfaces and the speed of the interfaces increases, as does the ability to process more and more traffic. The other thing you will notice is that several of the series, starting with the 320, have the designation M at the end of it. The M designation indicates that it's multi-OS capable. Those devices, the 320M, the 350M, etc., can be converted to run the Junos version of the Firewall software. It involves simply switching out the flash card where the OS is installed, and then it can run Junos, and it becomes an SRX series device once it has the Junos software on it. So those are convertible down the line if that becomes a desirable transition. The ISG line has the 1000 and the 2000. As you can see from the images, they have a very small one rack unit section on the bottom with the fixed interfaces in it, but they have expansion slots. So with the expansion slots, you can put different types of interface cards in there, and a large number of interfaces that can then expand in your data center line. The NS 5200 and 5400, also very expandable line. You can see the expansion slots and the the amount of traffic that these can handle are significantly more than the SSG line. This is how a typical enterprise deployment might look, where you would have remote IPsec VPN to remote offices, to a larger corporate device, either the NS or larger SSG series with multiple VLANs or perhaps even multiple vSYSs at the corporate headquarters or data center, connecting them together. So this is the typical enterprise environment. In the service provider environment, you have typical deploy of one physical system, and then you start breaking it up. VSys 1, VSys 2, and then your customers might have the SSG series out at their sites. So in your cloud-based system at the data center, you would have your large ISG or the NS series with the virtual system for each customer in the box, and they can hub and spoke IPsec VPN from your provider network. In addition to the firewall operations, there's a large scale of other Juniper products in the security space. The intrusion detection and prevention systems are available as not just a subscription service on the ScreenOS, but a dedicated appliance. These are generally used where you have a large amount of traffic that it would be difficult to process that as part of the firewall. So you can process them on a stateful on a separate appliance. Network and Security Manager is available as either an appliance or installable software on Red Hat Enterprise Linux in order to manage the ScreenOS devices and the IDP and other security devices. And the SSL VPN provides a more robust remote access solution. There is some remote access built in using the IPsec VPN and a client software on the firewalls for small operations, but the SSL VPN provides a more robust tunneled over 443 VPN access to a larger scale operation. And finally, there's the universal access control. These appliances are able to enforce at either layer 2 or layer 3 network access control. The ScreenOS product line is capable of being what is referred to as an infranet controller to deploy live policies against specific traffic. So with using the universal access control as a network access controller, you can identify specific users or specific devices, and then in real time rules are written on the firewall to only allow access to particular areas or traffic for those users. So this is an integrated suite of security products that Juniper provides in order to secure the network from one end to the other beyond the straight firewall operation. This is the enterprise portfolio. It's, of course, virtually impossible to read on this slide. So in the downloads for this session, there's a PDF version of this that's available from Juniper. This shows a very robust network with virtually all of the Juniper product line deployed, and how the different devices can relate to each other in the enterprise deployment portfolio. So we reached the end of Module 2 of this introduction to ScreenOS firewalls. What we did was describe the requirements that are necessary for a security device. We know firewalls have to provide the routing capability. They have to provide the ability for building sessions and operating on those sessions. They have to be able to do address and port translation, and they have to be able to do VPNs. We described then how those features get implemented in the ScreenOS architecture as a general overview. And we described how the packet flow works in the ScreenOS system, so that as it flows through and creates those sessions and processes that traffic. And then finally, we described how the deployment scenarios and the device options that you have in the ScreenOS system. So I thank you for your attention in this second module of the ScreenOS operating system. If you have any questions, you can post them publicly in the forum that's assigned to this class. I monitor that and participate there. Or you can use the links in the class to send me a private message if there's any in the material at all that's requires some clarification. I thank you very much for your time.